How about this one? What's the potential difference or voltage difference across a toaster with a resistance of 13.8? What is the name of that weird symbol? This is the what? This is the ohm, which measures what? Resistance. And with a current flowing through it with a value or a magnitude of 8.7 amperes. Did you do this one? Okay, so let's start. What givens do I have? Because that's the first thing you need to do. Because again, by the way, one thing about physics and math, there are so many equations, it's insane. There are full books of equations. If you don't know what you're given and then what you need to look for, you will have no idea what equation to use. So what am I given? Yes, the resistance. So what do you do according to proper solution technique? Right? What's the symbol for resistance? Capital R usually, yes. So you go capital R equals what? 13.8 in ohms. What else are you given? Electric current. What's the symbol for electric current? Not the unit, the electric. I. Capital I or small I. I'll use capital I. And it's 8.7 amps. Okay. Is there any scale change that needs to be done? Like, do we have any millis or megas or gigas or nanos? Nope. Everything is standard, which makes our life easy. What are you being asked for? What's the symbol for voltage? It's the only unit in physics where the symbol is the same thing as the unit. V for voltage and V for volts. So I am looking for V equals question mark. Okay, which triangle do I use? We have 4 triangles. Okay, Solomon? Okay, so basically this triangle. So this triangle. And might as well review how to use these kinds of triangles because some people had questions about them yesterday. Okay, so it's 3 compartments, 1 on top and 2 at the bottom. What goes on top? According to V. And the bottom? Either IR or RI, doesn't matter because they are on the same level. How do you use this triangle? Whatever you're trying to find, what do you do with it? You what? You hide it or cover it. Which one are we trying to find? V. So I cover it, and then you don't guess. You just do whatever the triangle tells you to do. What is the triangle telling you to do with these 2 things? They are on the same level, which means between them there's a multiplication sign. Done. So go ahead. V equals IR, which means 8.7 times 13.8 in volts. Who's got this? You have it? Okay, what do you have? Tell me all the numbers you have, and then we'll play with the sig figs. 120. Yeah, that makes sense. 8 times 13 is more than 100. What'd you say? 120.06. 120.06. What is the sig fig situation? Significant figure situation for, 1 second, for this. How many sig figs do we have here? We have how many? 3. All of them count. The 1 counts, the 3 counts, the 8 counts. How about here? 2. So my final answer, according to the sig fig rules we did, should should be how many sig figs? The highest or the lowest? You always go with the weakest link. You always go with your worst thing, which is 2. All right, what does that mean? I need to cut this after how many digits? 2. So I need to cut it right here. So is that what? Okay, now, does that 0 change the 2? Does that 0 change the 2? No, 0, 1, 2, 3, 4, don't change anything. 5, 6, 7, 8, 9, they bump up the number. So this will just be what? 120 volts. And that is indeed 2 sig figs. All right? Again, as maybe I mentioned before, sig figs are imported in university usually only when you do labs. I have yet to see a professor who cares about sig figs when you do what? When you do the calculations. Sometimes they tell you, oh, just round to 3 or just round to 2. Like the question will tell you what to do, like math questions, okay? However, when you do labs, which if you go to university for any technical field, biology, chemistry, physics, engineering, I'm sorry, you're going to have to do labs, which means the results then actually count. Okay? We're good? Okay? All right, perfect. Okay, let's go to the next slide. Okay, so tell me why What's up? Oh, there you go. Tell me why when you increase the what? What does it say? If you increase the voltage, the current will be higher. Oh, Raf, don't worry. There you go. Can someone reason to me why that happens? You can reason it from a mathematical way or from a conceptual way. Abdu? You what? You didn't change the what? You did not change this resistor. It's the same. All you did was what? Pump up the what? Pump up the voltage. When you pump up the voltage, what does that mean? Are you using a weaker battery or a stronger battery? Which means what? Are you providing less energy or more energy? Which means what's going to happen to the flow of electrons? Is it going to be diminished or increased? It's going to be what? It's going to be increased. Provided you don't change the what? Provided you don't change the what? Because what happens if you increase the voltage? Like if you go from a small battery, if you go from a 1.5 to a 6 volt, but you also increase the resistance. What could happen? Think. You increase this guy, but you also increase this one. Think. What's up? The battery goes up, the resistor goes up. What do you expect is going to happen to the current? Yeah, moment. Are you sure that's always going to happen? That's what I'm thinking. What? Give me all the possible cases. Maybe. What's the equation for Ohm's law? What equals what times what? The triangle we just used. V equals what? V equals I over V equals IR. I'm going to give you actually an interesting historical thing here. V equals I times R. Just so you know, George Ohm himself, the German physicist who actually came up with this equation, that's not the way he wrote it in his notes. That was not it. The way he actually did it was this. This is what he actually wrote. Is this the same thing? Yeah, because if you cross multiply that, what do you get back? You get V equals IR, right? What is he dividing by what? So the way he actually discovered resistance was that he kept what? Changing the voltage of the battery, and then measuring the what? Measuring the current and just dividing them. And he always noticed something very interesting. The R stayed the same. The R stayed the same. That's why some people memorize the resistance as a ratio. What's another name for ratio? What's every ratio? Fraction. Boom. Do you see the relation now? Resistance is a ratio between what and what? Between the voltage that you're providing and the what? And the current you're getting back. Okay? So to Momin's point. Momin, if I increase this one and I increase this one, what could happen to the current? It depends on the, yes, go ahead. Go ahead. It depends on the numbers I use, right? So for example, let's say this was 10. Give me two numbers that if you divide, you get 10. No. If you divide. No, 10 divided by 10 is 1. 110 or 20 and 2. 20 and 2. We're good so far? All right. Let's say I increase this to 40. I increase this to 40. Okay? What would be my new resistance? 40. Sorry, what would be my new current? 40 divided by what still gives you 10? 4, which makes sense, right? You upped your voltage, but you didn't do anything to the resistance. So you upped your what as well? You upped your current, right? But what if you make this one, for example, 40 divided by what gives you 20? Which means what? Your current did not change. Do you see what I mean? Anything could happen. What if I make this not 20? What if I make this 1? Sorry, 1. My bad. 40 divided by what gives you 1? 40 divided by what gives you 1? 40. So that means what? Your current increase. Do you see what I mean here? You can't just say, oh, I know what's going to happen. You need to be given some numbers. Okay? But if you keep this one the same, sorry, if you bump this one up and you keep this one the same, this has to increase to keep the ratio the same. That's basically it. All right? Very good. Okay. So this is basically what we call a PCB. PCB, printed circuit board. Printed circuit board. Basically, this is what's inside almost every single device. Your phones, your computers, your chargers, TV screens, every single thing. Okay? So the operation of the components would work fine until the recommended voltage maximum level. You increase that, boom, that's it. Why? Because when you increase the what? You increase the value of the voltage, but you keep the resistance the same. What happened to the current now? It's what? It's more current. Well, there's gonna be a certain amount of current before what? Before the whole thing what? Malfunctions, bursts into flame, whatever. It's like what? It's like when you have a water hose and you make the water pressure too high. What could happen to the hose itself? It could what? It could rip the actual body of the hose apart. That's exactly it. You exceed the pressure or the voltage in this case, you are ruining basically the entire circuit. Okay? All right. So let's think about this for a second. Pencils down here. How many batteries do you see here? How many batteries do you see? No, how many batteries do you see? You see just what? One battery or one voltage source. What's the strength of that voltage source? 9. This is the generic rectangular 9 volt. Okay. Okay. What is it connected to? Trace the wires and tell me what is it connected to. It's connected to a what? To a resistor, but also it's connected to something else. It's connected to a what? It's connected to something else. All right? How much is the battery providing? 9 volts. How much is this taking from the 9 volts? 3. So just by simple basic logic, how much is left to flow or to actually be measured across the resistors? Why 6? Because you're providing a maximum of how many volts anyway? 9. This one part of the circuit is stealing how much? Stealing how much? 3. You can't go wrong with saying that what? That the rest has to go through the what? Through the resistor. So how much is left? But that, oh, by the way, that also depends on one thing. Trace the circuit. By the way, how does the current go? Remember? Does it flow this way? Or like, is it going to go this way or this way? Who can tell me? Okay, Mumiza, what do you think? From the negative to the positive, but hold on. In the wires or through the battery? It is. See, that's the thing. It's from the negative terminal to the what? To the, because it always goes from negative to positive, right? But not in the wires. No, through the battery itself. You have a battery with 2 terminals. So that means what? Let's say, for example, that this is the negative. That means what? It's going to go from negative to what? To positive. Do you see what I mean? Okay, so always start from the negative, go through the battery. Technically, you're going this way. And then you go. So it's moving this way. So what's the only amount of voltage left to actually be measured across the resistor? How much? 6. Yep. Oh, this is something called typical LED forward voltage. So whenever you buy LEDs, which only has one single color to it, this is how much voltage is needed to produce that color. If you want to produce red, you have to use at least how much? 2 volts. Yellow, it's standard to use 2.1, 2.2, 3.5. Pure white, which is the combination of all colors of the rainbow, it's what? It's 3.2 volts. Okay? So, yep, 9. This much is what? 6. So go ahead and sketch this battery. And also sketch this right here. Okay. Yes. Where? Like here? No, nothing. It's just a rubber lid, just to make sure that you know what, no one touches it, basically. Yeah. Yeah. We don't really. This is just, or actually a lid, just to make sure that these wires do not just snap out. It doesn't really matter. They're connected already to the what? To the terminals. Okay. So as you're finishing up, what information do I know so far about this resistor? Okay. What was the first thing we figured out about it? How much voltage is measured across that resistor? 6 volts. And Ms. Hamidi then gave you the information that how much current is flowing through. 20 what? Milliamps. So what can we figure out now about the resistor? I know the voltage across it. I know the current through it. What's the only thing left out to actually figure out, Eva? So to find the resistor. Yes. Okay. By the way, do you already have the color code for the resistor? Okay, that's fine. But do you always trust 100% the color code? I would say probably not all the time, for a couple of reasons. Sometimes you can look at the color and not be sure if it's what, for example, orange or red, right? Because maybe it's been a long time and these colors have what? Have changed colors. So you can't trust it. The other thing as well is that, do you remember what the last band is called? Again, you never read the last band first, because the last band is either what or what. Only 2 colors are permitted for the last band, Mumiza. Gold or silver. And what does it tell you about the manufacturing of the resistor? Moment. Yes, the tolerance, the amount of error that you're free to exist within. Have you ever seen the plus minus sign? Like if you've ever done labs and you say, hey, what mass did you measure? Oh, I measured 5 plus or minus 0.1 kilogram. What does this mean? What does this mean in the words of, scientific experiments? 5 plus or minus 0.1 kilogram. What does that tell you? Yes, Abdul? Exactly. You are 5, but you could also be what? A maximum of how much? 5, yeah. 5.1 kilos. Or, what's 5 minus 0.1? 5, 4.9. Is it making sense? That's how they report things in experiment. Here's my value, and here's how much error I could actually live with. Okay? That's exactly it. Okay? So let's actually find the R. What's the equation again? Which triangle are we going to use? Which triangle? Yes, VIR. What am I trying to find? The V, the I, or the R? Come on. The R. So what do? I hide it. So I have to do what it tells me, V over I. All right. What's a small m, by the way? What's small ma? Come on, small ma. Like small mm or small ml. Ahmed? Milliamperes, like millimeter or milliliter and so on. So R equals V over I, which is how much? Is it 9 or 6? Are you sure? No, but hold on. What's that? Oh, go ahead. Oh, let me just 1 second. I just want to check that the recording is still happening. Yes. Should I use 9 for V or okay? How many people say I should use 9? Everyone, how many people say I should use 9 as the V? Moment, come on, own up to it, man. All right. Who else says 9? Okay, Reem, Yara, Eva. Who says something other than 9? Abdu. Why 6? Again, Moment. Is this the only thing in the circuit? Or is there another? So forget the battery. Is this the only thing that the battery is feeding? There's another what as well? There's an LED, which means what? This 3 is completely what? Not available for this. So what's the only, if I have a voltmeter and I connect it this way from 2 leads, how much would I measure across of this? 6, not what? By the way, what if I remove this guy? Then yes, the whole 9 is measured what? Across of it. Do you see what I mean? You always have to know how many things and how they're connected. All right, so it's 6 divided by, 6, come on. What's a milli? What's the power of 10 for the milli from the scale sheet I gave you? 10 to the negative 3. So you say 20 times 10 to the negative 3. All right? Now you can plug in the equation like this, or you can play with the 20 times 10 to the negative 3. What is 20 to the negative 3 in standard notation without the scientific? 0 point what? Is it 0, 2, 0, 0, 2, 0, 0, 0, 2? How many zeros do you need? 2 zeros. 2 zeros. So 0, 0, 2. 0.02 would be, oh, my bad. Sorry, you're right. I thought it was 2 times 10 to the negative 3. You're absolutely right. You're right. Sorry. Nice. Good catch. For some reason, I thought it was 2 millis, not 20 millis. You're right. So what would this be? Easy. What's 6 divided by 2? 3. But this is 0.02. So it's a what? It's 100 times bigger. So what is it? 300 in what unit? Ohm. This is how you do ohm. That's it. Done. This is something we're going to start using starting next week. Has anyone dealt with these before? Maybe in grade 9, because grade 10 they do optics, and grade 9 they do the circuits. Do you know what we call these things? These are not printed circuit boards. That's the advanced ones. What do you call this? Breadboards, okay? These are called the breadboards. How are they connected? Let me actually, hold on one second. Magnify right here. Do you know how they're connected? How? Yes, Tristan. Yeah, no, yeah, but how are the holes connected? Yes, there's the metal plate with the connections, but how are the holes connected? They're connected only what? Up, down, right, left. They're never connected what? Diagonally. No way. And you can tell by tracing this. Let's start with the what? Negative. And it goes into the what? Positive, and then it leaves the battery. So it leaves the red. Okay, check this out. By the way, what does this green represent? It's just a what? It's a wire. So the green is going, and then you basically pass it through this. What is this connected to? How many things? It's only connected to how many possible things? 4 things. Where? You could connect it up here, left, right, or what? Down. So that means what? Without you seeing it, there's a current going through this, right? Okay, so you keep tracing. This is connected to what? To that. It fully completes it. And then what? It could here, could be here, could be here. Nope, we chose here. Go. Right here. Where do you go from here? Up. You go through the diode. Oh, sorry, the LED. And then you what? You get down here. Where do you go then? Straight up. All the way. Up. Back to the negative terminal. Okay? This is how you connect a breadboard. You never connect it diagonally. Impossible. Okay? All right. Yes, these are the resistors we're going to be using in this course. We already have a pack in the prep room. So next week I'm going to start, handing them out. And yes. Sorry, say again. Ilsam? How do I know? Oh, but just, okay, I'll give you the battery. And from the battery, you'll just have to start tracing, and then you just go around. From anywhere, yes. But again, you have to start the battery. Because you start from what terminal on the battery? The what? The negative. And you go to the what? Positive. And then you leave the battery through the wiring, and then you come back to the negative. You see what I mean? So at any section of the circuit, you can know exactly if it's going this way or this way But you just have to see how the battery is feeding into it. But you have to start at the battery all the time. Because if you reverse the battery, what's going to happen to the current direction? It's going to what? So going this way, it just goes in the other direction. Yes? Oh, wires are connected to each other. Well, depends what kind of wires you use, everyone. We tend to make use of these wires. Sorry. These wires are very common in circuit experiments. You know what these are called? What does this look like? Seriously, I'm not kidding. Seriously, what does this look like? Crocodile, or what's the other name? Alligator. These are actually called alligator clips. When you actually buy them on Amazon, just write alligator clip wires and you will get these. So these are amazing because they actually what? Oh, they clip. Okay, so basically what you do is this. You know, obviously you can just connect it like this or like this. It depends how, but that's basically it. Is it making sense? So you can just make as long of a wire as easier. Yeah. They are almost the same material. Yeah, you just clip it like that, and now you know that it's a perfect connection.
But when you connect it to the board.
Oh, okay. The board already has what has metal inside of it. So once you clip this on it, like in the hole, actually the current goes through.
But why doesn't it go on the others?
Yes, but it has to be starting from the what? From the battery, and then it only sets one direction of flow.
Like, you know how it works with the resistor? How does it know to go through the resistor?
Oh, because the resistor is a metal. The resistor is not purely made of rubber. It's actually a metal. So it actually has to pass what? Has to pass the what?
So you have
The
to
current.
put metal?
Yes, of course. Again, if you touch something with a rubber glove, does it actually connect electricity or does it insulate it? It insulates it. So whenever you actually want to pass electricity, you have to use some metal or something wet, something with a polar what? With a polar connection in its chemistry. Yes, you've done chemistry. So polar means what? Some positive, some negative. Yes. You never read it from the gold or the silver side. Never. You read it from the other side. Always. Uh-huh. No, that's the thing. Everyone, listen up. Whenever you have a resistor, if you flip the resistor, a resistor has no direction. It has no, it's bi-directional. Okay, I see what you mean. Everyone, if I took the resistor and flipped it, nothing would happen. It would exactly stay the same. I see what you mean. The resistor does not have a what? Does not have a current direction. You see what I mean? It's perfectly neutral either way. It's just a chunk that the current is going through. It doesn't care if it's going through from the what? From the gold side to the non-gold side or the other way. Yes, go ahead. Yeah, makes sense. So that's the thing about resistors. They don't. What matters in the circuit is the what? Is the what determines the direction of the current flow? The battery. You flip the battery, you flip the entire thing. Does it make sense? You flip the resistor, nothing's going to happen to the brightness of light. You flip the actual what? Poles of the light bulb, nothing is going to happen. The battery or the voltage source is the most important because it's the one that has what? An excess of electrons on one side and a what? Deficiency of electrons on the other side. That's the only thing that matters. Yes. Say again? Oh, so instead of connecting it from the positive to the negative, let's say, for example, so let's say I connect these two. Come on. I'm just going to connect it like that. I connect this to the positive terminal of the battery and this to the negative side. How about if I flip the battery, like cross the wires this way? That's what I mean by flipping the poles or flipping the terminal. That's all. Okay? Are we good so far? Making sense? All right. So, okay, let's just talk a little bit about what's known as, which is the most important thing in devices, is power rating. Power rating. Every device, everyone just pencils down. Every device comes with a what? With a power rating. What's the power rating? How much power as a maximum amount of energy can it actually what? Can it actually handle? So for example, this is a what? This is a light bulb, what we call basically the what? The CFLs, okay? What's the power rating of it? How many watts? 23 watts. How about this radiator, for example? It's how many? It could handle up to 1,500 watts. How about this microwave? 1,200 watts. Okay, 1 second here. What's up? By the way, do you know what's the power rating of the regular white or yellow light bulbs you can buy from Walmart? Usually it's a fixed number. Have you ever looked into it? How much? No, more. 60. Always, you know. You go to Walmart right now and you look at them, usually they are 60. Okay? What do you measure using what? Come on. Power. Where's my thing? Okay. What's the equation for power? Come on. Rahaf, what's the equation for power? What's the triangle for power, which you will need tomorrow? What's here? Okay, Mumiza, tell me just what's the thing on the top? E, which stands for what? Capital E always is what? Energy. Someone give me one of the other two. Eva. Huh? T, time. Small t, never big T, small t. So what's left? P. So if you want to write this equation, what do you write? Yeah, you hide the P and you get what? You get the capital E over T. All right. What's the unit for energy? Not power. Power is measured in watts. What's the unit for energy? Yes? Joules. No, that's charge. That's the very first thing. Yes. So this is joules. And what's the unit for time? Standard seconds. And what's the unit for this guy again? So what does this mean? Everyone, check this out. I'm going to teach you a very good trick with units. Everyone, Rahaf, eyes on me. I'm going to take this one away. And what am I going to write in its place? Yep. What does this mean now? What does it mean that that light bulb had a power rating of 23 watts? What does that mean? For every single second of its operation time, how many joules does it need to operate fully? 23 joules. How do you read this? By the way, question for you. How do you read this? Read this. So 23 kilometers per hour. What does per mean? For every. So how would you read that? 23 joules per every what? Per every second. If you leave this light bulb on for every single second, you need to feed how much energy into it? 23 joules to what? By the way, it's a maximum power rating. So what if you feed 24 joules into it? What's going to happen to it? It's going to explode, or just what? Fuse down, or basically what? Just stop working. That's what power rating means. Do you see how power is related to energy now? It's how much you're feeding for every what? For every 1 second. How about this one? How much could it handle? 1500 what? Joules per second. Question for you. What if you give this one 1400 joules per second? Is it still going to work? Yeah. I mean, you can always handle what? Lower energy, less energy, but you can never handle what? More than maximum energy. And the maximum power rating is 23 joules per second for this one, 1500 joules per second for this one, and 1200 joules per second for this one. Now you understand the relation between power and energy. They're not the same, but they're so deeply related. Yes? Oh, okay. So, okay. You know what? Very good question. Could this technically be, everyone, guys, could this be technically a speed rating? Could you think of that as a speed rating? Yeah, you could. How will it be a speed rating? I don't know. Something could not be driven past what speed? According to that, 23 kilometers per hour. Do you see what I mean here? A rating is just a ratio between something and something else. It means you cannot exceed the top for every what? One thing of the bottom. Making sense? So if you're saying that my car's speed rating is what? 200 kilometers per hour, that means what? Do not go faster than what? 200 kilometers per hour. Otherwise, the engine might what? Might actually fail. That's basically what a power rating means. Sorry, what a rating means. You can have any rating you want as long as you understand what's on top and what's at the bottom. Make sense? That's what a rating is. Okay? Okay. This is a nice diagram. I like it because it relates by the way, honestly, that diagram right there, that summarizes all of electrical engineering. Really, electrical engineers all day are just concerned with 4 things. How much voltage is being provided? How much current is allowed to flow? How much resistance is what is being used? And how much what? power is being generated. That's electrical engineering. All of these 4 years of insane studying that Ms. Hamidi took, for example, at the end of the day, it's just to make sure that an electrical grid outside does not fail under the what? Under the operation of these 4 variables. Every single thing at the end of the day is basically what? You're swimming in the kingdom of VIRP. Okay? So electric power, all of these high voltage lines or high potential lines, is characterized by current flow and voltage to deliver energy in the form of what? Energy is always delivered in the form of power per second, joules per second, joules per second, okay? Power can be produced at any combination of current and voltage values. All of these insane circuits are just trying to understand VIRP at the end of the day. And by the way, I like this. This V is placed in between what? In between what? Yeah, because V is the voltage, and it only cares about the what? The positive and negative difference of the terminals of the battery. What about I? I is always something that what? That's what? No. Forget the direction. I is always something that's what? Flowing. I always moves. Current always moves. V is just what? There to provide energy, to provide potential. Current moves. R is just for what? R is just for a section of a circuit. The resistance of this section is whatever R is. P is what you get when you understand all of these 3. Okay? All right. Okay. So go ahead and write this down. Now, which ones you should write? Just write this one and this one. That's it. Again, all of this will be posted, so just write the first 2 statements. Yes? Yeah. So, electric power is the rate at which work is done or energy is delivered. Everyone, write this down as well. After work is done, it also means energy. Actually, I can say energy is delivered, but let's say energy is used up. Used up. Because that's how machines work. They use up energy. Unless you have a power plant, now you're what? Producing energy. So just these 2. Since the electrons get energy from the voltage source, battery, electric potential energy is measured in volts or joules per coulomb. Okay, joules per coulomb. Did we do this equation before? Yes, we did. This is this triangle. What do you measure using joules? Energy. So energy is here. What do you measure using coulombs? Coulombs. Huh? Charge, Q, yes. And what's missing here? It's the V. Yep. Voltage is equal to energy divided by charge. What about this one? Coulombs per second. That's this triangle. What do you measure using seconds? Time. What do you measure using coulombs? What do you measure using C? What do you measure using coulombs? Coulombs. What do you measure using coulombs? No, I is measured using amperes. Q, charge, yes. So, okay, so what's missing here? What is the division of Q and T? I, current, amperes. Yes, you got it. Okay, all right, let's go to the next slide. What was the physical symbol for power? Power. Capital P or small p? Never small p. Small p is used for something else, and if you take grade 12 physics, you will know it. Capital P is always standard for power as a symbol, not as a unit, as a symbol. Yes. No need to write this? Yes. Can you ever have, everyone, question for you. Can you ever have negative power? Can you ever have negative power? No, you can't. And why is that? What's the equation for power? What's the triangle for power? Come on. Power is down here. Two other things are up and down. What are they? Mumiza? Energy and? Could you ever have negative time? Could you ever have negative energy? So could you ever have negative power? You're basically dividing positive by positive. You are by default positive all the time. Good for you. Didn't we just do this? What did I tell you? 1 watt is 1 what? Joules per second. 1 joule per second. By the way, just so you know, everyone, do you think a single joule of energy, is a big amount of energy or a small amount of energy? Okay, let's see what people think. 1 joule of energy. If you're saying, if you're saying, I'm so tired, I burnt 1 joule of energy. What do you think? Do you think that's a big amount of energy or a small amount of energy? How many people say that a joule is a very small amount of energy? You're right. You know why? Because a calorie is 4 joules. A calorie is 4 joules. How big is a calorie? Seriously, if you eat 1 calorie, did you eat a lot of food or a very small amount of food? So if you ate 1 calorie, that's a very small amount of food. A calorie is how many joules? More than 4 slightly, 4.18. What does that mean? A joule is even what? Bigger or smaller? A joule is 1/4 of a calorie. A joule is 1/4 of a calorie. Okay? That's why sometimes when we do problems with joules, we always get what kind of numbers? Big numbers, because a meaningful amount of energy has got to be a lot of joules. 1 joule is almost nothing. You barely feel it. It's 1/4 of a calorie. Okay? All right. Yes. So this is some power rating. So a hair dryer, again, different brands could have different ratings, but in general, I guess these are the pictures that Ms. Hamidi chose. A hair dryer has 1875 watts. What does that mean? What's this word? Converting or using up 1875 joules for every what? For every single second of operation. Okay. All right, we did that. Okay, so now we have what? 2 equations for power. The first equation is what? What? Come on, everyone. Energy over what? So instead of W, I could just put what? Instead of E. So we again, no need to copy. I can put W or I can put capital E. Yes. Okay. However, we have another equation for what? Energy, relating it to what? Charge and everyone, guys. I'm relating the triangles together. What is this triangle is here, right? This triangle is what? E PT, right? What triangle is from here? E is equal to what? QV. Do you see what's going on here? E. What does that tell you? P times T must equal also what? Q times V, right? If this E is the same as this E, that means this multiplication also has to be equal to this multiplication. So I can derive or create this new equation. P times T is equal to what? Q times what? How can you solve this equation to isolate P? What do you do? Come on. How do you solve this equation just to solve for capital P? Abdul? Keep this here, and where do you put the T? Below. You divide the entire equation, both sides, by what? By the thing you don't want to appear on this side anymore. So P is equal to what? Q times B, all divided by T. Are we good so far? Okay. Everyone, check this out. What is this just by itself? What is that? What's Q divided by T? You see, I'm making you used to go in between the triangles. What's Q divided by T? I. What does that mean? This is math now, no physics. Boom. We just invented a new equation. Relating what to what to what? Relating power to what? Current, and to what? Voltage. Without caring for what? Do you see what I'm doing here? By the way, you need to get used to this, because if you ever take grade 11 functions, grade 12 functions, or grade 12 calculus, or grade 12 physics, you need to be good with what? With relating equations together, using one equation and another one, and feeding one into the other one, and creating something new. Okay, this is a very good skill. This is why I love teaching physics, because finally you make math make sense. That's the best thing about teaching physics. Truly, finally. Everyone says, oh, that's why we do cross multiplying. Oh, that's why we divide. Every dry, meaningless thing you learned in grade 9, 10, 11 math, now you're seeing, oh, okay, this is how we use it for meaningful purposes. Okay? All right, let's see the next slide. Hey, everyone. Check this out. Do we agree with this equation? What is the name of this equation? Ohm's law. However, I also know, we just know that what? P is equal to what? Okay, here's a question for you. What common variables are here and here? Tell me the two variables that appear in both equations. I's, and what does that mean? I can use one equation to substitute. Okay, so V is equal to what? Ri. But there's a V here. So what could I replace this V with? You see? Replace this with that. Is it making sense? Again, you're planting one equation into the other. What's I times I? What's X times X? What's A times A? What happens when you multiply a variable by itself? Heck, what happens when you multiply a number by itself? Square it. So what's I times I? I squared. Still times what? Still times R. It did not go away. Here's the third equation. Do you see how many equations we're coming up with? Why is, by the way, you might ask, why are you giving us so many? Like, we're confused. This is not for the sake of confusion. This is for the sake of what? Of having everything you need and just looking at, oh, I don't have to do a two-step calculation anymore. Okay, question for you. If you didn't have this equation, you would have to use this one first and then plug it into this one, right? You would have to say V equals whatever this times that, get that value, and then feed it into here. But now you can go straight from what? From what? I and R to what? You do not even need to care about what? V anymore. You see what I mean? That's why you can go straight without having to do a two-step calculation, or sometimes even more, a three-step calculation. Okay, can we invent another equation? Yes, we can. There are three equations for power, by the way. P equals IV, P equals I squared R. Here's the third one. Check this out. Do you agree that this is correct? Do you agree that this is still correct? But what am I going to replace now? I'm not going to replace the V. No, we already replaced the V before, remember? The V was replaced with I times R. Now I'm going to replace the what? The I with what? Done. Ladies and gentlemen, we have so many equations now relating P, V, I, and R. Done. Okay? One last thing, come on. A DC motor, by the way, does anyone know what the DC means and AC mean? DC means direct current. It means the current stays the same the whole time. AC is basically these things. Alternating current. They vibrate 60 times a second, 60 hertz, okay? So a DC motor, what does it do? Okay, find the what? Find the current. Okay, let's think about this. What information do you know about it? And come on, you have a lot of numbers. Some of them are meaningless to you. By the way, that's what they do in physics. I give you so many things, and I see who can understand what's important and what's not. Solomon? What thing here do you think is of importance to us? Power. What else do I know? And what am I asked for? Current. Okay, what equation do I use? Come on. I have power. How much is my power? Come on. 5. What does kilo mean? 1,000. So you can just write 5,000 watts. How much is my voltage? 72 volts. I need what? What equation relates P, V, and I? The easiest power equation. P equals I times what? What am I trying to solve for? I. So what do I do here? It's a triangle. Again, this is a triangle. You can always create the triangle. P, I, V. Which one am I trying to find? So what do I hide? So how much is that? 5,000 divided by what? 72. How much is that roughly? 70 something. Go ahead. Give me the answer. $69.4 in what unit? It's current. Thank you. Amps. Done. I'll upload this and you can just do this at home.